Okay, today we're going to look at section 2.6, De Morgan's laws. So here's what we're looking at. According to De Morgan's law of negation of a conjunction, the negation of P and Q is equivalent to the negation of P or the negation of Q. And De Morgan's law for negation of a disjunction is the negation of P or Q is equivalent to the negation of P and the negation of Q. And the negation of a conditional can be negation, not an explanation point. So the negation of if P then Q is the negation of is equivalent to the negation of P and the negation of Q. And writing a conditional as a disjunction, we have if P or Q is equivalent to C. This is the symbol for equivalence. What this does, the Morgan's laws allows us to write the negation of conjunctions and disjunctions without using this phrase, it is not the case that, to indicate the parentheses. Avoiding this phrase often results in written or verbal statement that is clearer or easier to understand. So we want to write the negation of each statement in words without using the phrase, it is not the case. So here I have Jackie played softball or she ran track. So this is an or statement right here. And we want negation. So if we say Jackie played softball is P, or she ran track is Q, we're looking at the negation of P. Jackie did not play softball. And then we're going to an and then negation of Q. He did not run track. Okay, so what do we have here? We have Brandon studied for a certification exam, and he passed the exam, or he passed his exam. So again, if we label this first statement P and this Q, we're looking at an and statement here, and we want to negate it. So we're looking at not P or not Q. So Brandon did not study for his certification exam, or he did not pass the exam. Fairly simple. So let's look at this. The negation of any condition or any statement has the opposite truth values of the original statement. The negation of the conditional is the conjunction of P and not Q, or P and not Q. Consider the truth table below for the negation of a conditional. So as you see, we have our P and Q, and the conditional is only false when P is true and Q is false. So in this case, the negation of that would be false everywhere except there. So as we said, the only time the negation of a conditional statement is true is when P is true and Q is false. That means the negation of if P then Q is logically equivalent to P and not Q, as the following truth table demonstrates. So let's look at this. Write the negation of each statement. If Edna Mode makes a superhero costume, then it will not include a cape. So again, if we label this first statement P and Q, I'm looking at if then. So I'm looking at this, and I want to negate that. And let's double check. So it's P and not Q. So Edna Mode makes a new superhero costume. And negation of P, it includes a cape. If I had pancakes for breakfast, then I used maple syrup. Again, looking at this as P and Q. So we have I had pancakes for breakfast. And we're changing this to an and. I did not, negating Q, use maple syrup. So now we're going to write the negation of more conditional statements. If some people like ice cream, then ice cream makers will profit. So, again, first statement stays the same. Some people like ice cream. But ice cream makers will not make a profit. So we're negating ice cream makers will make a profit. And we're using the but connector here instead. If Raquel cannot play video games, then nobody will play video games. So we say Raquel cannot play video games. But somebody will play video games. So the first statement stays the same. Second statement, we write the negation of it. So we can look at some properties that hold true for number systems and sets also hold true for logical statements. Following table summarizes some of the most useful properties for analyzing and constructing logical arguments. So we have an example of the commutative property where P and Q is equivalent to Q and P. Also, P or Q is equivalent to Q or P. We have where we can look at either one first. We can look at P and Q first, and then and R, or we can look at P and Q and R. Same thing here with distributive. We're looking at P and Q and R. So it can be P and Q or P and R. And then we have De Morgan's, which we've already gone over. So let's look at write the negation of each conditional statement applying De Morgan's law. If Eric needs to replace the light bulb, then Marcus left the light on all night or Dan broke the bulb. So we're looking here. And we want to take the negation of this. So we start off with P being the same. Eric needs to replace the light bulb. And we go with the and. Then we're gonna negate. Marcus did not leave the light on. And Dan did not break the light bulb. And Dan did not break the light bulb. So we have P, then Q, where Q is Q or R, and it breaks down like that. Then let's look at another example of this. If Trenton went to school and Regina went to work, then America cleaned the house. So again, our first statement stays the same. Trenton went to school. And Regina went to work. And we're going to negate here. America did not clean the house. So let's not take this for granted. Let's look at it and see that it's true. So we're going to construct a truth table to verify De Morgan's law for the negation of a disjunction. So essentially what we're going to try to see is if this is the same as this, because that's what De Morgan's law says. So we'll do this the same as any truth table. Start out with our P's, true, false, true, false. We're going to need the negation of P, so false, false, true, true, and the negation of true or Q, false, true, false, true. So now I'm looking at P and Q. When is P and Q true? And the only time a and statement is true is when both are true, which is right here. The rest of them, P and Q is false. Okay? Now we want the negation of that, so we're simply going to change true to false and false to true. Now we're looking at not P and not Q. So now we're looking here, and when are they both true? This is a typo. This is supposed to be or. It's right there. Which changes this drastically. So let's go back to an or. An or statement is true when one or the other is true. That means this has to be an or as well. So one of them's true here, but both are false here. So this changes to false, 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 true. Now we are looking at and the only time, again, looking at not P and not Q, the only time an and statement is true is when they're both true, which is here. The rest of them, it's false. And as you can see, this and this are the same. So they are equivalent. And we've just shown that De Morgan's law is accurate. And that finishes up 2.6.